something called a Lewis dot symbol.
What chapter?
We're on chapters 8 and 9. That's what this next test will cover. And that handout, we're going to get to that handout, y'all, but let me give you a little bit of background before we can start working through that handout that I gave you. There's a worksheet on that. What we're going to do with Lewis dot symbols, y'all, is we're going to use dots to represent valence electrons. So if we start with, we'll do the third period elements. Sodium is in the third period. This is sodium's Lewis dot symbol. I only have one dot because sodium only has one valence electron. Magnesium. I'm going to draw magnesium's Lewis dot symbol like this. It does not matter if you do it like I have it drawn there, or if you do like that. I'm trying to get them so you can see them. It doesn't matter if you put one on the left, one on the right, or if you put one on the side and one on the top. Okay? Moving across to aluminum. Here's aluminum's Lewis dot symbol. Why does it have 3 dots? Because it has 3 valence electrons. All right, in every element, you need to envision that it's got 4 sides on the element. Okay, so you've got 4 sides to put dots on. Moving over to silica. At this point, you guys can probably draw what that looks like, right? I've got 4 dots. Now, I'm going to go down here and write phosphorus, sulfur, chlorine, and argon. How many valence electrons does phosphorus have? It has 5. Watch how you draw them. 1, 2, 3, 4, 5. After I've got 1 on each side, now I've got to start pairing them up. Okay? Sulfur would have 6. 1, 2, 3, 4, 5, 6. Chlorine would have 7. 1, 2, 3, 4, 5, 6, 7. And how many does argon have? 8. Okay, so that's what the Lewis dot symbols for the elements look like. There's actually a good bit of information you can get from a Lewis dot symbol. Can y'all tell me what the octet rule says? We have not talked about an octet rule, but I'm guessing that some of y'all have heard octet rule before.
Is that where every 8th element has a relationship?
Okay, that's the law of octaves is what you're doing.
You can only have 8 valence electrons in each shell.
Right. Y'all see octet's got something to do with 8. Yeah? That makes sense to us. The octet rule, that actually does say rule. Got a little happy on my U, but the octet rule says that atoms will gain, lose, or share electrons to end up with 8 valence electrons. So they're either going to gain electrons to have 8, they're going to lose electrons so that they'll only have 8, or they're going to share electrons with somebody else so they can all have 8. So atoms gain, lose, or share electrons to end up with 8 valence electrons. If we go back and we look at the Lewis dot symbols, y'all, argon is a noble gas. And we've said that noble gases don't like to react. They're inert. How many electrons does it have? Valence. It has 8. See, it doesn't want to lose any, doesn't want to gain any, and it doesn't want to share them. It wants to be left alone. It's not going to react. Now, if you look at these other symbols, Any place where you have two electrons together, that's called an electron pair. And so that area wants to be left alone because they're already paired up. But any place where you have an electron by itself, that's a lone, L-O-N-E, a lone electron. So if we look at chlorine, for example, chlorine has an electron by itself right here. Chlorine wants to do something about that. It either wants to gain another one. If chlorine gains one electron, doesn't that make it the chloride ion? Right? What kind of charge does chlorine like to have? It likes to be -1. Would it ever be -2? Well, look what happens when it gains one electron, y'all. It's got its octet. So it doesn't need to gain another one. What kind of charge does sulfur like to have? -2. Can you see that from here? That makes sense because sulfur could gain an electron here, and that would give it a -2 charge. How many would phosphorus? 3. It would like to gain 3. Okay? Now, does sodium, does it want to gain electrons? Does it want to be negatively charged? It wants to be positively charged. What kind of charge does sodium want to have? +1. How's it going to get to be +1? It's going to get rid of one electron, and it'll have a +1 charge. Magnesium has 2 electrons that it can get rid of, hence it likes to have a +2 charge. Aluminum, +3. Silica is kind of special. It's one of those metalloids. Remember the stair step that separates the metals, which like to be positive, from non-metals, which can be negative, and the metalloids. Silica is not really going to give its electrons away. It's not going to take 4 on. Silica, what it's going to do is it's probably going to share these with somebody else, and in sharing those, it's going to give it 8 electrons. Because it would share this 1 electron with an electron from somebody else, and they would share those 2. They would share 2 here, 2 here, 2 here, and that would give silica 8. Okay, but we'll talk more about that sharing in a minute. So if we can look at the Lewis symbols, y'all, before I started adding all these electrons to it. Any place there's 1 electron by itself, that's a good indicator of the number of bonds that atom can form. For example, chlorine typically will form 1 bond with somebody else. Do you see that if this is the Lewis dot symbol for chlorine, which has 7 valence electrons, wouldn't everything in group 17 have 7 valence electrons? Right? So wouldn't everything in group 17 have this Lewis dot symbol? You're just going to have a different symbol in the middle, whether it's fluorine or chlorine or bromine or iodine. So I can see that everything in group 17 will like to form just 1 bond. Everything in group 16 is going to have a Lewis dot symbol that looks like this, that looks like sulfur. How many bonds will it typically want to form? 2. Group 15 would want to form 3 bonds. Now, is that going to be always and forever? That chlorine and those things are only going to form 1 and everything in the next group, sulfur, 2, etc.? No, but that's sometimes a good indicator for us to look at. That will not always be the case, but it's a good gauge to remember. Okay? Now, we've got different types of compounds, and we've talked about these early on when we were naming. And you guys know there's a difference between an ionic compound. Tell me what you remember about ionic compounds.
Metal, non-metal.
Ionic compounds are metal and a non-metal. Give me an example of an ionic compound.
Sodium chloride.
Sodium chloride. And we know a lot more about ionic compounds. Remember when we started learning the rules of naming them, and then we talked about them being electrolytes because of how they dissolve in solution? Remember all that? Okay. Sodium chloride's our example, but what I'm going to talk about with sodium chloride would apply to any ionic compound. It's formed from the metal, sodium, which is a cation, and the non-metal, chloride, which is an anion. We just looked at it when we were doing Lewis dot symbols. How does sodium get a +1 charge? It has to lose an electron. How does chlorine get a -1 charge? It gains an electron. Okay, sodium loses an electron. Where does it go? It goes to chlorine. Likewise, if we were looking at magnesium chloride, y'all, what's the formula for magnesium chloride? It's MgCl2. And we learned, how come that 2's there? Because I taught you guys swap and drop, right? Swap and drop. But if you look at magnesium's Lewis dot symbol being this, and chlorine's Lewis dot symbol being that, magnesium has 2 electrons to lose. But that chlorine can only accommodate one of those. So I have to have another chlorine to accommodate the other one. And so now you can see even more why it's MgCl2. It's swap and drop, but that's why it is what it is. Okay? Now, what kind of bond are we talking about here? Yes, these are ionic compounds, and we know that. But what kind of bond is it? Y'all, ionic compounds have ionic bonds. That's pretty easy. So what does that mean? For a bond to be an ionic bond? In ionic bonds, electrons are transferred. In an ionic bond, electrons are transferred. And that's what we just talked about on that previous slide. How does sodium get to be a +1 charge? It gives up an electron. How does chlorine get to be -1? It gains an electron. That's an electron being transferred. Okay? Now, ionic compounds. That's kind of a little small summary of what we know about them. What's the other kind of compounds? Okay, they're actually, we call them molecular compounds. But what kind of bonds do they have? That's covalent. Molecular compounds have covalent bonds.
What's molecular again?
How do you know if a compound's molecular? Okay, ionic's a metal and a nonmetal. Molecular are all nonmetals. Remember that? Yeah? Okay, molecular is all nonmetals. Can you think of an example of a molecular compound? Okay, nitrate, the polyatomic ion nitrate's molecular because it's made of nitrogens and oxygens. Water, that's a molecular compound. Okay, hydroxide. Yeah, any of the polyatomic ions themselves are molecular, but when you combine them with another metal, they become ionic. Salt. Okay, I knew you were. Sugar.
CO2.
Carbon dioxide. Okay, those are molecular. They have covalent bonds. What does that mean?
Share.
In covalent bonds, electrons are shared. So guys, what we will draw for covalent bonds and for molecular compounds, like if X was one of our elements and Y was another element, then when we draw a line between them, that line is the bond. That line represents 2 electrons. And our idea for a covalent bond is that X and Y are sharing those 2 electrons. And what we're going to eventually encounter, guys, when we're always supposed to share. Do we share equally? No. Okay, guess what? Elements don't share equally either. And we'll talk about that later. How are they not equal? Well, that goes back to electronegativity. Sound familiar? It should. Okay.